Bart has asked me to introduce myself because according to him, I'm better at that than he is. Unfortunately, Bart is a little bit better than I am because he's got that natural modesty that comes along with being Belgian, or Flemish in particular. And I got the natural loudness that comes along with a Dutchman who isn't, inhibited by anything. So I'm going to keep the introduction short because otherwise I'll just go into some long, rah-rah bragging session. And so I am a control theory guy. Started off a long time ago here, then went to the States, MIT first, then Berkeley, and then I quit the whole thing and I ran a hedge fund in New York. I did that for some years. Then I retired myself, but I hated it, and the retirement, that is. And then I went back and I started putting together what I've learned, my background in control systems and controls, and what I've learned in finance and economics, real hands-on knowledge. I try to put this all together. And here you see where I've come up to now with this. And this is a really nice talk for me because it combines several topics that are really my favorites. And the one is differential geometry. To me, that's like the queen of all math. And I'm a big math freak, but that's it, Now, what I don't like about differential geometry, that people will, math guys will write books on differential geometry that are this big, and there's not a single picture in it, okay? Maybe a commutative diagram, okay? That's the best they can do. So I'm going to take a different approach. I spent quite a bit of time on this presentation. Not because of the ideas, but just because I had to learn how to use TIX or TIX-Z in order to make these pictures. And the second thing it combines is analytical mechanics. So that's the mechanics of Lagrange and Hamilton. And I also have always been fascinated by this and how you can generalize things to relativity, quantum mechanics, and go beyond. It's really a beautiful piece of work. And then recently, the researchers have been putting these together. It's all done very abstractly. It's absolutely inaccessible unless you're like nuts, like I maybe am, right? And then please come in, sorry. Yeah? And then the last thing that I, of course, like is what I now call economics. I don't like to call it finance because I feel, it's broader. Finance is too much of an emphasis on money, which, of course, I have, but I don't want to say it. All right? So, try to get the Belgian in me out. So I'm going to get going. And first, I'm going to talk a little bit about what I'm not going to talk about. All right? So just to say where we stood. And that is something we've been calling economic engineering. Now, Lagrange's approach was built on Newton's. All right, so Newton's comes with his law, and it builds on Aristotle's idea. And Aristotle kind of had the wrong idea, and everybody with him, that a velocity is caused by a force. So you needed a force to maintain the velocity. And Newton is the first to say, no, you don't. The thing will move by itself, okay? And if you want to change the velocity, that's where you need a force, all right? This is the critical insight. So F is m times A, not F is m times V, right? There is a thing that's proportional to V, and that's momentum, all right? Now, this same mistake, I feel it's a mistake, all right? Maybe it is not a mistake. It's another way of looking at it. But if you view it as a mistake, then I can say this same mistake is made in economics. So in economics, what is a velocity? It's a flow of goods, right? It can be securities, can be water, it could be apples, I don't know what, all right? And what maintains this flow of goods? Well, it's some kind of inertia, and this inertia we call demand, all right? And how does it do that? Well, an economist will say because of a price that acts on it. All right. And then it will say this equilibrium comes when these prices are equal. All right. Now, this is not right. For them, maybe it is right, because just like Aristotle, they'll be able to calculate some equilibrium way in which fire goes up and water goes down or something, and earth goes down even faster, right? But it's not quite right if you want to do mechanics, and especially your mechatronics project where you want to look at movement. All right, so you need the concept of a force that changes that quantity, that flow quantity. All right, and it's the balance of forces that causes equilibrium, not the balance of prices. Okay, all right. So we need a concept of force. And what is the economic concept of force? We call it a want or a desire, or in Nederlands een behoefte. Huh? What is that? Well, if we follow Newton, we'll just say this thing is forcing the price to change. So if I want something, I'm going to be willing to pay more for it. All right? And that's Newton's law right here. I want something, I'm going to pay more for it. All right? Huh? That's the whole idea. Now, then you need some kind of definition of momentum. So here it is, P is M times V. So this is now the price. This is the quantity demanded. This is what we call a supply line or a demand line. It goes the other way. The only reason it goes down is because for economists, the price is not a vector, right? So it can only take positive values. So otherwise, if you have it a vector, you can make it a nice, here's the demand and here's the supply. All right? So that's the idea. Okay? So what does an economic force do? What does a want do? It just allows you to move along. Economists will call this a movement along the supply line. And then you expand your demand, that's the acceleration, and you increase your price exactly with the amount of the force. All right? That's it. Okay? Now, with that law, you can basically do mechatronics, but then economechatronics, because this is Faraday's law, so you can build your circuit. Here's a circuit. So we developed something called economic network theory. That's together with Kuhn-Hutters. So you can build these whole networks, and then you use these Kirchhoff laws for physical clearing for the current law, and then for the mesh law you use there's a price clearing, right? Because the magnetic flux here becomes the price. It causes that change. Huh? And then you can see this as a market, and then you can define these elements. These are two inductors in series, so these are two suppliers that are in a supply line, all right? These guys are demanders. They are in parallel, so they compete. Huh? These are the storage facilities also competing. So when you do them in parallel, they compete. And when you do them in series, you can work it all out, all right? And then you can create arbitrary networks. So these are two markets. Maybe this is apples, this is pears. And then this mutual inductance tells you what the price effect is. Huh? So one market, you'll have this price, that's given by the demander, but he demands in both markets. And his demand for this will do that. And you'll get this elasticity tensor. That's your inductance tensor here, and you can get it all worked out. All right? Huh? So that's what I'm not going to talk about. But that's the background. Huh? Now, what's wrong with this, right? Now, nothing really. You can just build your stuff, but you just got to memorize all these laws and what these things do and all these Kirchhoff laws, and I don't know what. You just do network theory. But it is a little bit, you always get this question like, why would this be right? Okay? Huh? That's also a bit of trouble with Newton's. How do you know this is correct? All right? And maybe you don't, because maybe you don't have a linear demand line, and maybe you don't have any mass, and I don't know, like light didn't have it, and no mass, but you still have momentum, and so you need to take a more general point of view, and that is exactly what Lagrangian mechanics give you. And I want to just motivate it here. So there's a shift of perspective. So what does the Newtonian approach do? It's like a differential equation, and you say, all right, I do this, and that causes that, and that causes that, and then you look back and you figure this out, and you have this whole causal chain. But that's not how you set up a Lagrangian. It is like you have one thing that you minimize, the action, all right? And boom, that will give you everything, all right? Just plug it in. Now, for an economic perspective, this is already nice because it's causal, but this thing is more what I would call purposeful. You have a purpose to do this. Now, for a particle, it's kind of dumb to think that it has a purpose of minimizing something. Why would it want to do that? But for an agent, an economic agent, it's very useful. It's just maximizing utility, all right? Okay? It makes sense. Now, why would you do that? Wow, no reason. And in fact, that's what economists say is the basis of all economics. So if we just see Lagrangian mechanics as a way of maximizing utility in a general sense, this should always work. All right? We can't. And then what we want to do is build it up from there and then see how we get this Newtonian description of demand and everything. All right? There's another thing, when you look at this Newtonian approach or this network theory approach, you have all these agents and you got to sort it all out and put them together. This thing takes a system view. We look at the whole thing in one shot, all right? And then try to figure out how the chips fall. So instead of all these laws, you just have this one principle. And here's the thing that I feel is really important. This is where the differential geometry comes in. One of the problems with the Newtonian approach is that it's so coordinate dependent. What is your x coordinate? What is your y? How do you choose these generalized coordinates? You can take whatever you like. And you've got these big matrices and vectors and subscripts up, to the sky. All right? But at a certain point, it becomes very hard because the way you do your coordinates and your record keeping becomes an inextricable part of the model. And what you really want to do is keep the model independent of how you choose these coordinates. This is also called invariant or confusingly covariance. And it's kind of an approach that was started by Einstein. So he says, okay, junk all this. We're just going to look at space-time rather than giving all kinds of rules for how time goes. And there's that, looking at it in one structure, called space-time. And then we endow it with some kind of manifold structure, and we endow it with some other stuff. And then you can choose coordinates how you want. You can write it. You can do all your subscripts how you want. All right? Don't say matrix, say tensor. Don't say vector. If you don't mean it, if you mean covector, if you mean one form, that's the idea of invariance. So these are real because they're independent of the coordinate system. All right? Now, for economics, we're going to see that the independence is of the record keeping, how you do the books. All right? So this is going to launch me in here. I have a little quote here from Ernst Mach. He's the guy from the Mach number. He was a philosopher who was behind Einstein's big change of how to look at nature. And he uses his word economical. He means something different a little bit. He means that it's an economic way of thinking, that you don't have to keep track of all these things. But I nevertheless think that it's, that's what you do in economics. We just want to be economic about our money, all right, and our values. So let's go do it. So I want to do two approaches. One is the regular differential manifold approach, which is just what an accountant would look at. And the second one, what I want to do is the extended manifolds. This is some hot new stuff with contact manifolds, etc. And that's how your trader would look at it. It will be journaling, all right? And that's where the exciting stuff is, all right? So I'm a little bit ambitious here, but I hope to get through it. All right, so let's start with the bookkeeping. Now, this is the setup. So an economic system is a differentiable manifold, and here it is. So what do you have? You have a bunch of goods, say apples and pears. So then I have a two-dimensional manifold. All right, here it is. These are the different stocks I have. So I'll open my cupboard, boom, I have that, right? I haven't said yet how I'm going to represent it. I just have that, all right? This is the physical reality. Then I'm busy trading. So I'm buying and selling this stuff, or acquiring and disposing of it. So I'm increasing this stock or decreasing it. So boom, I got a vector here, that gives me how much I'm doing, right? That's the velocity normally. Here, that's your demand. That's the quantity you demand, all right? Now, this vector doesn't live in this space because it's got totally different units. It's so many apples per time. So it's got to live in another space, and that's the velocity space, or what we call the tangent space, right? So it's just a flat space right on top. This is a nice vector space. This is just a space of points, but the points are close together. So you can see it's continuous, and you can change it smoothly, right? That makes this thing a differential manifold. I want to give some examples of when it's curvy. All right, so that's the setup. All right, now, then you can start doing stuff, right? And what do when you do stuff is you start with this stock and you end up here halfway over there, right? And you buy. This guy's only buying, all right? I could look back, all right? Now, how would you describe that in differential manifolds? Well, you take a function, I'm going to call this function the course of action, and you take time as a real axis here, and just map it right in there, right? Huh? Okay. Huh? So you'll see that this demand vector is just a unit of time forward. Huh? All right. Huh? And then you want to keep track of what you're doing. So what you do then is you do the bookkeeping. Now, suppose these are stocks of money. I have a project with the bank, Rabobank, and we look at those things. Then the way you keep track of it is by using an accountant, and they have two statements they use. One is what they call a balance sheet. So it just keeps track of these balances of what you have, so much money or so many pairs, I don't care, right? And the other is what they call a cash flow statement or just a general flow statement. All right? These are what I call the books. You can also use a profit or loss statement if you want, if it's on accrual basis. All right? Huh? All right? So you see, this is a coordinate chart. This is what's called the chart of coordinate chart. But these are the accounts that the accountant chooses. He is accountant. He chooses accounts. He can choose them the way he wants. All right? They do. And that choice is called a chart of accounts. I mean, some of this is amazing, huh? That what an accountant calls a chart of accounts is called a coordinate chart in geometry and in mechanics. All right? Huh? So this is just an accountant setup of an economic situation, and this is just some CEO, kind of doing his trading, and this is the CFO, keeping track of it. All right? Now, there's one little element here, is what I haven't discussed. This is this little circle here that's called a Lagrangian. And what you want to do is find out how good you're doing, right? Huh? And this thing is just going to keep track of your benefits, the utility you're requiring, right? We're actually going to take a negative point of view because it just works out better. So we're going to look at this cost, all right? But it's just generalized economic cost. So how much do I dislike it? It's a sort of disutility, all right? And I represented it like a circle here, all right? Huh? We'll talk about that later. First, let me give you some nice examples of how you get these curvy manifolds. So here is one example. So this is a mortgage. So this is your amount of your mortgage. These are your interest payments. So you start paying interest, you go this way, but you start paying off, and then you end up going in a circle, right? So a mortgage agreement says that you gotta stay within this circle here, all right? Huh? So that's what we call a holonomical constraint, and it leads to, this is the stock space. So there's two stocks. There's the stock of your amount of money that you invested still, and then the stock of interest that has been paid, all right? Huh? Okay. Then you can look at a savings account. That's a growth thing. So you're getting all this interest, but every time it gets reinvested, and then you grow up like hyperbolically like that. If you do that, you get an exponential growth, all right? This is also sort of an exponential growth with an imaginary exponent, right? Huh? This is in between. If you have some land, the land really doesn't produce, become any bigger. It just gives you the crop, and it's just producing. All right, huh? But anyway, this is will be a flat manifold. This is a more hyperbolic-looking manifold. All right, huh? And they come out of these hyperbolic constraints. So far, so good. This is what economists do too. But before I go on, you could have two mortgages, right? Here one, here one. All right, then you get a sphere, huh? All right, huh? So then you can plot this little Lagrangian on there. That's called an indicatrix, and it tells you, if you look at your course of action, how much distance you've traveled, right? And you can make a map. That's the coordinate chart. That's your balance sheet, right? Huh? And you can make various ones. This is, I think, the Mercator. This is some BMR. I don't even know. Huh? All right. So all I wanted to show you that it's kind of intuitive, because you start seeing this manifold, the base manifold, as being the Earth, and your trading is just traveling, and you're minimizing here, you're minimizing distance, but maybe you minimize something else. It all depends on, this is called an indicatrix in mapping. And then the maps become your books, right? Huh? You can also combine a growth. So you have an interest, you have a savings account, and you have a mortgage with the bank. So you have one circular one and one hyperbolic one. You get these kind of things. Huh? This is a pseudosphere. It gives you hyperbolic geometry. This is it's called in the chart. It's called the Poincaré disk. Very famous. All right. So just a little wow whiz and how natural these comes and how we can use all this. This is more of a 19th century geometry that preceded differential geometry. You just use it and you can just see here, you know, chicken with eggs or mortgages with interest or cows with milk. I don't know. Huh? All right. Very natural. Let's move on. Now, I want to take one word and say how economists then solve this. All right, so economists don't have any dynamics. But nevertheless, they need to predict how markets are moving. This is based on a paper I got from Rabo, which is for the CPB. They have a model for the housing market. It's big to do now because nobody knows what's going to happen, whether we're going to get a crash or this. So they have this model. So this is their house, and these are the housing services you get. And then they feel that these houses are increasing exponentially, you know. Huh? I don't know how these houses do that, huh? But whatever, huh? They'll build that in. And they also build in the rates at which the services are delivered, all right? Huh? Now, this is not a holonomical straight. This is a non-holonomical straight, right? So if you specify a velocity. Now, what they end up doing by doing this is they totally specify the movement. All right, but it's all done kinematically. There's no dynamics. There's no forces. All right, you see them piling it on, right? Huh? Boom, boom, another. Here a subsidy. Here this. Here. So this is the way they solve everything using non-holonomical straights. This kinematic solution. This is what we don't want to do. We want to do dynamics. You know, we're mechanical engineers. We want to write Newton's law, and instead of specifying everything, we want to derive it based on motive forces. All right. Huh? Okay, so how do we do that? Well, what we do is we use this little device here, this Lagrangian. All right. This is our running cost. Okay. And here I plotted it. This is a circle. Huh? And here I plotted your quantity demanded. Huh? And here I showed you how you can derive this other thing that's called a covector from that. So this is sometimes called a Riemannian manifold. This is the metric tensor, all right? Yeah? And then this is a vector, and with it belongs a covector. Yeah? So if you saturate the metric tensor with this vector, you get a covector. Now, what is this covector economically? I know what it is, it's momentum, but what is the covector economically? Well, these are my running costs. This is how fast I'm going. So this is telling me how much cost I'm accumulating by unit of how fast I'm going. That's the price. Okay? That's the price. So it's just the amount, the cost you make per unit of motion, right? And here I show you that you can construct this price purely geometrically. You don't need any formulas. All right, there's no formulas here. All right, okay. This thing has a name. It's called the tautological one form, and it's really the offer price. It's the price you're willing to pay for it. All right, huh? All right, we're in business. All right, huh? But you don't need this Euclidean metric. So you can use something like this, then you get substitution effects because the direction will matter, right? Huh? So if I start demanding more apples than pears, all of a sudden, they start influencing each other. Huh? Then I can use degenerate ones. There's one direction is always, I don't care about, the zero, right? Huh? So now it's really not a Riemannian manifold anymore. It's totally degenerate, but it still works. And then you can do these hyperbolic things. This is very useful. Huh? We'll see later. But a lot of indifference curves and things like that in economics are like that, So the more pairs you have, the less, if you have one less pair, you have not so many, you want more apples, right? So you can still construct this price. That's what I'm saying. All right? This is the price. So the running cost, this Lagrangian allows us just to define what price is. Now, this is a big step because economists don't. So they define equilibrium in terms of price equality, and they define price in terms of equilibrium. So it's circular. It's not circular. and it's invariant. You know, so it's a property of a person, not of the way you're doing the bookkeeping. Well, I wrote it like this, P and Q. If you take away the Q and look what it is, then it's going to depend on what accounts you've chosen. All right, so now we can do something else. Instead of plotting the limit, we can now plot all these prices, right? So we have the same stock amount here, and then instead of the quantity I'm buying, I'm just plotting the price. Now, the price is also a vector. It's a covector or one form. So it also is in a sort of tangent space, but it's called cotangent space, and that's all the prices, right? So the prices are given by two levels. It's like a level line. So if you walk on a mountain, you know, you have two things, how fast you're going and how far, you know, how steep the mountain is. All right, so this is what you, So there you are. So there's another space called the cotangent bundle where you put these together. And you can also make a chart out of that. So you just have some inventory report here that tells you how much stock is. And then usually when you get these, there's a catalog that tells you what's going inventory report. So the catalog is what goods you have. The inventory report is how much you have in store. And the price list tells you what the prices are. That's over here. So if you go to Albert Heijn or a grocery store, that's exactly what you see, right? You go, you see in the shelf, this is so much in stock there, so much in stock there, and attached to it underneath is the price. You can't switch the prices. Well, you can, but you'll get into trouble, right? So associated with every stock is a one form that gives you the price. That's the idea, right? It's simple. You know, this stuff takes forever, but once you have an economic picture, it's just obvious. I'm just walking in the grocery store. All right? Okay. I want to keep moving because now, okay, I made all these nice definitions, but what am I going to do with it? I still want to figure out what I'm supposed to do. All right? So what am I going to do? Is I'm going to look at the cost optimal activity, so the maximum amount of utility. I'm going to take this path, you know, I'm going to look at all these paths and see how I can accumulate the most benefit to me or the least cost. All right? This is also called cost-benefit analysis. And this is done with calculus of variations. All right? Now, calculus of variation is also something that I've never really understood until I finally figured out what was going on. So what you do is you just look at these running costs and you just look over the interval at which you're trading. You say, this is my time interval. You know, this is the end period. This is the beginning. I have some option. It's expiring then. I don't care, right? And then I can calculate this thing. It's called the action in mechanics. It's called the length if you look at a geodesic. And it's just called the period utility, right, or cost. All right? And I want to minimize that, so I'm going to set that. I'm going to vary it around. So I'm going to pick this different courses of action. I'm going to vary them. Here's a little variation of it. So what is called these variations? They're called what-if scenarios. All right? So you say to yourself, what if this? What if that? So that's all the calculus of variations is. So a whole pile of what-if scenarios to do our cost-benefit analysis. All right? That's it. Now, so you go wiggle this thing around, and you wiggle it here, then you bring the wiggling inside. So you've got all these partial derivatives. This is what economists will call marginal cost, right? So the marginal cost if I increase my stock, and the marginal cost if I increase the amount I'm buying, all right? Now, these are names. This is going to be scarcity, the force of scarcity, and this is going to be another way of seeing the price, all right? So here I just repeated it. So and this thing here, the marginal cost, if I increase the amount demanded, that's called the canonical momentum. That's the price. It's a little different price than what I had before because I got a Q dot here. All right, we'll talk about that. And then this thing, what does it say is how much do I like having a little bit more in stock? Or how much do I dislike being a little bit short? Okay. So that's the potential force. But that measures, you see, your stock measures how scarce the goods are to you. All right? That's clear. If your cupboard is bare or you're short, it's even worse. You're out. So you want to drive this up. So what you got to see is that the potential force, that is exactly what we would call the force of scarcity. Okay, now it's going to drive the price through this Euler-Lagrange equation like I promised it would, but let's just go and do that. All right? Huh? Before I do that, I want to solve a big problem, because the way this gets solved in mechanics is they do this trick called integration by parts. Okay? It's just integration by parts, and they'll throw that in, right? Huh? That's this trick here. Okay? And what you end up doing, you get, you can get this, you can get rid of this guy over here, the change in the quantity demanded. All right? Huh? But it's always a little bit magic. I want to spend a little bit of time on what that has done. All right? Maybe too much. The price, so that we have to know, we have now kind of two definitions of price. And we got to show that they end up to be equal. This is the problem here. The real price that we had before is this one here. Because I have a little lot that's DQ, and I offer it for sale with at a price P. And here's everybody else. Huh? So you collect them. This is called the order book. Huh? If you trade stock, this is the order book. This is like NASDAQ level 3 will tell you what it is. All right. And then you can look at it. It starts moving up and down. Huh? All right. But this is not the price that an economist looks at. Economist looks at something called a Walrasian auction, where they see prices balancing demand and supply. So they sit and wiggle this flow here, this Q dot, and then they see how they can get those to match. That's different than just, just selling it. Why are those the same? All right. All right. The problem with this one is it's in the cotangent bundle of the tangent bundle. This really sucks. All right. Huh? This swing is nicely in the cotangent bundle, and we keep track of it. Here, we would need another statement. We would need an acceleration statement or something to make this happen. Now, what you do is, what a trader does, and I know that because I did it, you start looking how the order book changes, right? So that you look at the liquidity, this thing goes down, this thing goes up. So you start looking at the time derivative of these orders, all right? Now, I chain ruled my way through there. So it's composed of two things. First, what is called the cost accrual. So whatever that order is, the amount, I have to multiply it by how much the price got worth more, right? To look at this change. And the other is the marginal benefit of asking for a little bit more, right? That's this guy, at this price. But now I have an expression that I can use here to put that in, and that's all I need, right? Okay, so this is the integration by parts trick, but totally natural. All right, this is a long outstanding problem because nobody has been able to find a Walrasian auction. This is how Walras defined it. This is what they use to determine price, but they're sitting in the cotangent bundle of the tangent bundle. It sucks to be there. All right, this is the way to do it through the integration by parts trick. So I didn't want to. I didn't want to withhold that because I'm here telling you about differential geometry and how cool it is. All right. Now, let's just go plug it in. So now I can do the minimization. I plug everything in. This thing goes to 0 because the paths, they all begin at the same position, end at the same position. I'm not varying that. And then I get the Euler-Lagrange equation, and it basically says that my force of the scarcity determines the change in price. So the scarcity stuff is, with abundant it is, the price goes either up and down. If it's scarce, I jack up the price. If it's abundant, I bring down the price. This is Newton's law, right? It's the law of demand. So now we got it from a very general principle, right? All right? We don't even need masses in anything. It's just there. All right? This is true for something that has no mass. All right? But nevertheless, you can plug this in. So here is a Lagrangian. This is the typical one you use in for these kind of systems, right? What is this? These are your direct costs. So this is the stuff you're purchasing, right? These are a quadratic cost function in that. I just chose some constants here. These are the benefits of actually holding it, for having an inventory. It's also quadratic. And then I calculate these partial derivatives. So the marginal cost then, well, you just bring the 2 down and you get the supply line. And here you get what we call a storage law, right? This tells you how convenient it is to have something or inconvenient. All right? So that just rolls out. And then you can see this is just a trader. This one is buy selling, and this is a storage. Huh? All right. Huh? Here is Marshall. He's kind of the inventor of the theory of demand of this picture. So if you think of this if you think of this as a supply line, you can see that the rent here, what is it? The expenses, those are the costs. This has a name for cost. So that's the kinetic co-energy here, and this will be the kinetic energy, right? So that's this term is the integral of this line if this thing was straight. All right? Huh? So they do that. He calls it producer's expensive. I call it direct cost. It's just slightly more general because a demander is the same thing. All right? Huh? And they don't really look at that stuff. Huh? So that's the problem, right? So you only have a mass moving, it's going to stay in equilibrium. Well, sure, what could you do? Huh? You need some forces to change it. All right. Okay. So that's what I want to show there. I still have a little bit of time left. So I want to this is the interesting part, so I want to blow through it. Okay? So now we're going to take the perspective, which is harder differential geometrically, but easier if you're a trader. All right? And what a trader does, they have a blotter. Or if you do labor services, you have a timesheet. You just go and you say, okay, I clock in on this day, and I did so many. I did so many. Units of labor, or I bought so many shares. All right, okay. And then I have another day, and then I index this. All right, so my blotter, I just go and keep track of this. It's called a journal. All right. So now I have a couple more things. So not only can I keep track of the stock, but I can also say how fast real time is moving with respect to my journaling time. All right. So when the market closes, I stop. I stop my indexing, so the derivative of real time, this one becomes zero. Right. I can adjust it. I can do all kinds of things. All right. This is called an extended phase space. All right. Now I can choose this index the way I want. There's some clever ways you can do. I don't want to go into it too much. This should have been, but this is one way to do it. It's called the proper time. So it just the running costs become a constant. It's really easy. This is another way. It's called bundle reduction. You use one of the stocks to index what's going on. And the one we're going to use, of course, is money. We have one good, it's called money, and then we index everything in money, we get rid of time, and we have monetized it. All right, I also don't want to talk about that. But the framework is very, very general. All right? Now, what do you get? You get a new manifold that looks like the old one, but it's a little bit bigger. So there's one stock quantity and one time. I can't draw more than that, right? So time is all part of this, and we call it an event. Right? And then here's also a tangent space, and that gives you the flow of time, right? And how fast time is going and how fast the stock is going. So maybe in an accident, time goes a little slower, because the events go faster. So all you do is you reorder by the event rate, all right? And you choose a fancy event, okay? So this is also called logging. This is what a trader does, all right? But this fits in what's called the extended bundle, all right? And you can also figure out what the price is. So here I have one, and it now depends not only on the stock and how fast the stock is flowing with respect to the indexes. So I use a little different derivative, but also how fast time is moving, okay? So you can actually calculate what the price of time is. You just take that same partial derivative, right? So it's the marginal cost of time, the flow of time. And if you do that, you can get this. The total price becomes the price of the goods plus the price of time. And we define the negative E as being the same, all right? It's just the negative of the price of time. So it's the benefit of time, the marginal benefit of time, all right? This thing is called the Poincare-Cockton integral invariant. Is what I would call the total price, okay? I can calculate what the price of time is. And that's interesting. You get this expression. People may recognize this as a Lagrange transform, but it's just saying I have the revenue, I subtract the cost. Okay, what do I get? Profit, right? So it's the negative of the surplus, economic surplus, it's also called. All right, yeah? The negative, it's a negative, and then you can calculate the power. That's how much surplus you're allocating. And then you get two Euler-Lagrange equations, one for the momentum here, that's the price, and one for the energy here, and that's the surplus. All right, huh? So it's very super easy now. So those are the two great conservation laws that we can apply to economics. Okay, let's keep moving and use this. I want to have two slides, this one and that one. The last one is the best. What I can do now is I can look at, say, labor services or housing services. So you have you're working, but you can't work more than 24 hours a day. So there's a maximum rate. You have a house, but you can't rent it out for more than 24 hours a day. So there's a maximum rate at which this can be done. All right. This does not fit in the Newtonian model of a supply line where you just keep increasing the supply. But you can take this extended journaling thing. So you put time here. So that's just this guy, right? And then you find a Lagrangian that tells you what is equally crappy for you if you're working, all right? And of course, the harder you're working, the worse it gets. So it kind of slants upward. And then when you have to work 24 hours a day, it's infinitely bad, all right? This is called the light cone. And this is just this kind of hyperbola. Now you can work your way through it. And then you'll just get a Euler-Lagrange equation. So you'll get that the price elasticity is modified a little bit. But this is called the Lorentz factor. So it's a premium you have to pay. Huh? And this tells you then what the surplus is. So you'll see that it's the old surplus plus some constant term here, right? That's the revenue you get if you were working 24 hours a day. Yeah? So MC is the price. And the price of the price times C. Okay, boom. So then you can calculate what your price is. Here's what you get, right? So you see that when this person has to work 24 hours a day, you're never be able to pay him enough. This is the main line. All right? Huh? Okay. So that's relativity in the slide. Then my last slide, and I'm going really fast because all the work is done, is what I call engineerization. So you can actually, you see, this works fine with the Lagrangian exposure, storage, and this demand here, but this sucks. This is just a force, all right? But now we can, because things are going over time, now we can fix this. We can define a new variable that's called the cost basis. We have another thing, the discount rate, that's just the damping rate, okay? And I make a new Lagrangian where I just plot this in. So I'm saying, okay, the total cost basis, the amount of money I have outlay, is being multiplied by this rate of discount, okay? I cycle through then I can calculate the discount factor. I can calculate just a bunch of stuff here. I can calculate, this is called the carry. That's just the scarcity plus all the stuff I pay this broker because he's going to discount the price while I move the stuff. All right, that's the damping. Put it all together, and I get this familiar equation, and you can figure out that you get your damp sinusoids and stuff. All right, huh? So this is kind of a nice point to stop because what did I do here? I was able to get something that normally is done with a Rayleigh dissipation function right endogenously into a Lagrangian. And it was pretty effortless. Huh? Hope I didn't screw up the TU computer by throwing this water on it. Yeah? Sorry, bud. And at the same time, this is my last slide. So I just made it. So I guess we have 4.3 minutes for questions. Huh? Yes. Huh?
this the beginning thing the Lagrange approach, right? Where
Yeah.
you had this metric on the space of goods or something, this Q.
Yeah, the space of flows, right? Huh?
Do you have things like non-holonomic constraints? Do they make sense also?
Yeah, you don't hold economic constraints.
Non-integral, right?
Yeah, so you just have to. It makes sense. You can do that, right? Huh?
I mean, from an economic modeling, are there like systems where?
Sure. Yeah. So if the contract really specifies that you have to make this payment at that time, it's just a non-holonomic constraint. The problem is if you pile on so many that there is nothing left anymore, then you don't need to bother with any dynamics. All right. So what's going to happen? Your prices will all stay constant because the dynamics gives you the price adjustments. Okay. That's all that happens. It's like if you have a robot and you kinematically constrain everything, you have a controller and your mechatronics project or whatever projects, and you make it so that it precisely does this. Well, yeah, there's no, but these Euler-Lagrange equation that gives you the energy and the momentum, you can ditch them because your controller will just become infinitely hot, or do some infinite forces in order to keep that price, that momentum at that point. That will be your problem, huh? You see, huh? I mean, how do you get a robot to do exactly a certain movement, in disregard for the mass of its limbs or anything, right? Huh? Only by having infinite amount of energy. Huh?
Yeah. I'm just thinking, right, that you can only move in certain directions, right?
Well, sure. Yeah.
Maybe by maneuvering well, right?
Yeah. So you have a coin, yes. But the only thing you shouldn't do is like constrain the whole thing. That's what economists do, right? Huh? That's all I'm saying. Of course you can. Yeah. It makes total sense. Huh? Yeah. Yes. Yeah.
How do I actually come up?
Yeah.
Getting correct economic laws very.
This is the problem, right? So suppose I take an arbitrary mechanical system. How do I come up with the correct Lagrangian? It's exactly the same question. That's not so easy. And in fact, if you want to do that, you're probably better off just building something like this, which is what we do. Huh? Okay. Huh? And then you can show that those equations of motion, you can backtrack what your Lagrangian should be. All right. So you can go both ways. Huh? So if you have a Lagrangian, you can figure out the equation of motion, but the other way you can do too. So if you have a system, you can like recalculate what the Lagrangian is, and you say to the economist, well, this is what you're doing. That's how I would use it. Huh? Yeah.
How hard is the learning the correct Lagrangian so that you get the market activity that you observe in the past? Like how hard is the learning process?
It's just a question of engineering design. So how hard it is to build a system like this, right? Huh? So you can't just use the data and say, hey, I'm going to make a model in this approach, right? So you got to come up with some dynamical system, a real one, right? Not just a bunch of differential equations. You have to be in the phase space somewhere, right? Or in the state space, okay? So there's got to be a momentum and there's got to be a position, and they have to be conjugate. So that's what you do. You just have to draw this up, right? And then you can use the data to fit the parameters, right? Huh? It's just classic engineering. Don't overthink this in terms of, neural nets, AI, right? This is just a bunch of guys with overalls on and grease underneath. This is just a regular, huh? I know where you're trying to go, but this Lagrangian is just telling you what the equations of motion are, not the way we do that with having already what you see a lot of controls is that the equations of motions are imposed on the Lagrangian as a set of constraints, okay? And then this Lagrangian is in addition another optimization thing that you want to do, and then figure out what this controller should do, all right? But that's not the perspective here. Here, everything is a Lagrangian, and then you try to figure out what the optimal behavior is. So the equations of motions have to roll out, huh? Okay, huh? So, can't get too fancy with this stuff, huh? Yes.
So with this, do you think that banks will start contracting engineers instead of economists?
Yeah. Well, they already are.
Yeah.
Yeah. I think they've been making offers to my students, and and now it's still in the experimental phase. It's very frustrating because you would think, look, this is better. You know, get rid of these economists. Well, why is it? It's not that they're bad, but they always look at equilibrium. And the problem is things have become volatile in energy markets, in financial markets. And they don't deal with volatility. We do. We have time differential equations, you know? Okay. So we can, if you think of price equal to momentum, you can calculate, and you have an economic force, you can calculate how these prices should move. You need a model, you need all this stuff. All right. And they just never have thought of that, you know? So and they're sitting there and they're trying to make these models, but they're all kinematic models. You see, they're lacking the dynamic aspects, the kinetics, right? So my answer to you is as soon as they realize this is the only way to get dynamics, that's when they start hiring engineers instead of economists. If they're just interested in equilibrium like the government is, so the government has the CPB, all they want to know is if we do this, what's going to happen in the long run? In the short run, whatever. All right. Okay. So the moment you get interested in the short run, that's when you need a mechanical engineer, right? Okay. Or electrical engineer, because we're about movement. Okay. That's my answer. But it takes I can't get it. You know. Just having trouble. So one of the problems was the Newtonian approach is very clever. If you have an engineer, it just works. But they will say, well, how do I know this is correct? Right? Then I say, well, this is why it's correct. Because this is your utility function. You know, this is the price of time, and this is the price of the goods. All right? That's energy, and that is momentum. So, yes. So it's frustrating. But I think that's the future. Engineers doing, I call it economic engineering for this reason. You know, it's not engineering, it's not economics, it's engineering. Not engineering economics, but economic, mechanical engineering, electrical engineering.
Goes with time, Max.
Yeah,
And if there are
thank
any
you.
further questions, you can always stop.
Yeah, that's all.